So welcome to this session, which could have been called Apocalypse Now. So I will talk to you about the consequences of climate change.
Well, not now right away, to be honest. There is a part that will wait a bit. So, last time I told you about the dynamics at work in what we commonly refer to as climate change. So there is one thing I didn't quite finish during my overview of last time, because in the substances that humans put into the atmosphere, there are of course the greenhouse gases that I have told you about at length, but there is also another category of substances which men put into the atmosphere, which is called aerosols and aerosol precursors. So an aerosol, in physical language, is simply a suspension in the air of liquid or solid particles. So all of the people in this room who've ever swept a broom, if there are any, to whom it happened, yes? Well, you have created an aerosol on this occasion, since you have created a suspension in the air of solid particles if you swept a bit vigorously. In the elements that man puts into the atmosphere and which can create suspensions in the air, you actually have both elements that are emitted directly as liquids or solids and which will then create suspensions. For example, soot. Soot is a suspension in the air of carbon particles, and so it's part of the aerosols. And then you have substances that will create the aerosols once in the air, meaning that it is emitted in the gaseous form, and once it is in the air, then the reaction takes place, which will turn the chemicals into liquid and solid particles. And so in there you have a very important category, which is sulfur dioxide, SO2, which once in the atmosphere will create sulfate particles, which are shiny and particularly reflective particles to sunlight. And so there is this peculiarity, for example, that the particularly sulfur-containing fuels which are used by the merchant navy have a short-term cooling effect which is greater than its heating effect. And I do say short-term because aerosols end up being purged from the atmosphere, in particular by precipitation. For example, for sulfur aerosols, it ends up giving acid rain. The sulfate dissolves in water when there is water, and that makes a little sulfuric acid that we like a lot once it gets to us on the ground. And so you also have another effect which is important in the effects of aerosols, which is that these small liquid or solid particles can be used as nucleation nuclei to promote the condensation of water vapor to form clouds. And we realized in particular that above zones that are very highly industrialized, the clouds that form are made up of particles which are a little thinner and which precipitate a little less easily. So it has an effect not necessarily on the cloud cover, but on the other hand, on the behavior of this cloud cover, it has an effect. So human emissions can also modify a little the nature of clouds that we will find above our heads. When the emitted particles, so I come back to soot, are black, obviously that intensifies the heating because it increases the amount of solar radiation absorbed. On the other hand, when the particles are shiny, typically like the sulfates, it's the other way around. It will increase the albedo and therefore decrease the amount of solar radiation absorbed by the surface. So these aerosols can have a warming or cooling effect depending on their nature, but overall, they all share the characteristic of being short-lived species, all right? They are all species which will have an influence on the energy exchanges in the atmosphere, which are reasonably short-term effects. So here you have an overview of the different substances that are emitted in the atmosphere and which have an effect essentially on the reflection of the solar radiation, except for soot or la suie in French or black carbon. So there, but otherwise, for the most part, it's in quotes short-term cooling effects. This graph, which you find in just about every edition of the IPCC report, makes at that moment an assessment of all the warming and cooling effects of all substances that humanity puts into the atmosphere. So the unit that we use to make the radiative balance of the atmosphere is watts per square meter. We could have used just watts, since the atmosphere has a given contact area with the ground, which is known, which is the surface of the Earth. But in this case, rather than carrying around multiples of watts with 10 to the power of 12 all over the place. In fact, we prefer to think about it in terms of watts per square meter. So if you remember from last time, or actually if you don't remember, well, maybe because I didn't say it, but the order of magnitude of the solar radiation reaching the ground is 200 watts per square meter. It's a little more than that, but that's the right order of magnitude. And the order of magnitude of the natural greenhouse effects is a little less, 170 from memory, watts per square meters. And the additional greenhouse effect is of the order of 2 to 3 watts per square meter, if we do the plus and minus effect in total. So here you have the plus effects, in particular greenhouse gases with long life expectancy. Here you have a whole bunch of effects, a little more or a little less. And here you have the results with the error bar, which you see there. And you see that the error bar mainly comes from the aerosol part. All right, this is mainly where the error bar comes from. So the overall effects of humans on the energy exchanges between the atmosphere and the surface of the Earth is indeed a positive forcing effect, that is to say that we add energy, but you have in the story, again, the aerosols that have an effect which is negative, but with a poorly evaluated magnitude for a certain number of them. So once we know we have warming and cooling effects, I will now explain the logic of a climate simulation. The logic of a climate simulation requires putting two things as input of the simulation. It asks to put as input the representation of the physical system, therefore a climate model, and it asks to put as input the hypothesis with which we are going to disturb this physical system, that is to say the emissions. So historically, and I kept my presentation this way because historically that's how it was done, and it has changed now, but I'll explain how. So historically, the path that was presented was as follows. We do a hypothesis on greenhouse gas emissions. This hypothesis is itself conditioned by economic and other hypotheses like population, etc. And that leads to having possible trajectories with regard to future emissions. So take note of one important thing. It is that in the resulting emissions scenario, the emissions result from the economy, which calls energy. And so compared to what I explained to you in the first lesson, there is an inversion in causality in the way of doing the scenario, since normally you have energy, and that gives you both emissions and economy, all right? The real input assumption is not economy, which calls energy, but energy, which leads to economic value and emissions and economy. So we should have two outputs from the same input, which are GDP and emissions, not emissions as an output of GDP. Is it clear or not? Crystal clear, I suppose. This is exactly what I explained in the first lesson. However, the emission scenarios are made by economists who therefore refers the cause and who tell you that there is GDP and that this GDP calls for energy, or rather they mix up the limiting factor, more precisely. So you have emission scenarios and those emissions go up and down. These are hypotheses by definition. Once you have emissions, you put that into a first stage of modeling, so there you already have modeling, in which you have evolutions of the greenhouse gas concentration. Because, in fact, the real forcing of the climate is the evolution of the greenhouse gas concentration. If you have increasing emissions and at the same time you have the sinks that increase, your concentration does not move and therefore there is no forcing of the climate system. For there to be a forcing of the climate system, it is necessary that the thickness of a blanket increases, that is to say, the concentration. So today, in the reports that are presented by the IPCC, what you have is directly evolutions on the concentration. So when you see RCP written somewhere nowadays in the scientific documents that talk about climate simulations, that means representative concentration pathway. And so it is directly assumptions that are made on the evolution of concentration. And from there, we derive the possible emission scenarios. This evolution in concentration is therefore given to be eaten up by a climate model, and this climate model will say ouch more or less strongly, and it will tell you how it suffers the ouch. Okay, so we'll spend a lot of time today watching this. So we'll tell you it's heating up, it's burning here, it cools down there, it hurts, and here I take a flood, there a hurricane. Well, for hurricanes it's a little more complicated, and so on. So the climate model will tell you what it sees in the evolution of the climate system. In the more advanced models now, there is a feedback between the concentration and the climate model. So for example, if you have a climate that drifts too quickly so the ecosystems cannot keep up, some of the CO2 sinks are weakened, and so ecosystems die, and so you have less photosynthesis and the CO2 is less well taken from the atmosphere. And so with identical emissions, you have the concentration that increases more quickly. All right? Well, these dependency phenomena are taken into account in the most recent models. On the other hand, what even the most recent models do not take into account and will, in my opinion, never take into account, even those that pretend that they do comply with the economy, is feedback on the input hypotheses. That is to say that there is no model that tells you there the climate system has started to drift so quickly that it is not compatible with the fact that we maintain the current GDP. All right? There is not a single climate model that tells you that. With, therefore, this peculiarity, or this oddity, let's say, which is that the simulations that give you the most unpleasant results when it comes to global warming go with the most important emission scenarios, which in the way they are written today also go with the economy, which is doing the best. So we have something a little surprising, which is that the more the climate system deteriorates, the better is the economy. That's what you got chronologically in the way that today simulations are done. I repeat, or is it clear? All right? We need the biggest emissions, so the economy in the story is told that is doing the best, so that the climate gets worse, which is another way of saying that the climate can never, in the way that the simulations are done, damage the economic system by construction. All right? So what emissions will be is obviously impossible to predict. I don't know how to predict how many men there will be in 40 years. I don't know how to predict how much oil there will be per person, or how much gas or coal per person. I don't know how to predict how much people will eat meat per person. All I can say is that if it's terribly different from what is happening today, it's that a disaster will have already taken care of quickly regulating the system. That's the only thing I can say, but otherwise, I can't predict it. So what people who do simulations do is that since they don't know how to predict, well, they do scenarios. So they take several possibilities. And in what I'm going to show you from now on, the results will always be conditioned on the hypothesis that was taken as input. All right? So once again, this is something essential. It must be understood that the results that you will see from now on are always conditioned on the emissions. And therefore, since I think I will not give the same exam again this year, one of the reasons why it is impossible to predict accurately the risks of climate change is notably because it is impossible to predict accurately what the emissions will be. I asked the question to your friends last year, why is it impossible to accurately predict the risks of climate change? And I think only 1 in 5 in the copies that I already managed to correct, which managed to get that it was because the emissions are not predictable. There, so either the other 4 were sleeping or they weren't in good shape that day. But there, so since we cannot predict the emissions, we will never be able to accurately predict the consequences, all right? So here is what a perspective of the first stage of a modelization gives. This is to say, moving from emissions to concentration. Once again, I remind you that nowadays we are going backwards. So first we have the RCP, and from that we derive the possible trajectories in emissions. This is how it's done nowadays. And so you have here, therefore, a perspective of concentration. Here, in fact, of the most important of them, CO2 in the air. We have the one that you had before we started playing with internal combustion engines and steam engines. The one that began to deform until the end of the 20th century. And here you have the possible evolutions during the 21st century. But you see that these possible evolutions are very different according to the emission scenarios. So the low scenario, up to now, I take it as emissions which remain constant. So in fact, I would have to present to you the 1.5 degree scenario, let's say. In fact, the 1.5 degree scenario, basically, that's what we already emitted. So if it's not the emissions that will remain constant, it's emissions that go to zero tomorrow morning. This is the 1.5 degree scenario. From emissions that remain constant up to emissions that are greatly increased. So until now, I used to call this the Polish of the year 2000 scenario. So why Polish of the year 2000? Because the Pole is the European who still relies the most on coal in proportion. And what remains to be extracted from the ground is, above all, coal. And moreover, from the year 2000, because this scenario corresponds to the effective consumption of 10 billion Earthlings who would use the same per person amount of energy as the pole today. So that's why I called it like that. And it helps to visualize in socio-economic terms the meaning of such an emission scenario. So in fact, it only means a humanity of 10 billion individuals who considered that what is acceptable, what is normal, what is standard, let's say, is to live like a pole of the year 2000. If we have that, both in terms of energy consumption and technical performance, we arrive at an emission scenario that gives you this CO2 concentration at the end of the 21st century, to give you an idea. So once we have an evolution of the CO2 concentration, we then put it in a climate model. So what is a climate model? It's a virtual planet. Instead of being flight simulator, it's climate simulator. And this virtual planet, which is therefore a digital model which runs on a computer, is necessarily a discrete model because you know that even very powerful computers don't like infinity. All they can do is manage a finite number of operations or a finite number of points. Yes? I mean, we can always find worse scenarios. I mean, there's no problem. I'm just saying that this one actually corresponds to a poll of the year 2000 applied to 10 billion people. I mean, I chose that. It's to illustrate. Because since you still have today a standard of living which is higher than that of a poll, so what I'm saying is that if 10 billion Earthlings want to live a little worse off than you, this is what it gives in terms of emission scenario, or rather, at the level of material comfort that you have today, to be more precise, and this is what it represents in terms of emissions and therefore in terms of concentration. It was to illustrate that. So I was saying a climate model is a digital representation of the planet. It's a model, and so by construction, it is something that is discrete. So there are grids. So the way it works is that we cut out all the fluid compartments of the planet into shoeboxes, that is to say in parallelepipeds, or almost because they're a bit curved. But these are parallelepipeds for clowns or for people with very flat feet, because typically the length on the horizontal is a few tens to 100 kilometer, so we will say 100 kilometer in orders of magnitude, and on the vertical the thickness is rather 100 meters, so it's very, very flat feet. But otherwise, that's the idea. We're going to cut the atmosphere and the ocean into shoeboxes, and we will, as far as the ground is concerned, represent it with grids there as well, with exchange properties with the atmosphere which are different depending on whether it is water or land, obviously. These models have been sophisticated over time, but all are based on the basic equations of physics. And one important thing, which may be surprising at first because we say to ourselves, hey, that's not how we usually do experiments. But one thing which is very important to know is that what we look at with these models is how they converge with a given greenhouse gas concentrations and how do I... It doesn't depend on the initial state with which we parameterize them. In other words, these models, whether the mean temperature at year 0 is either 15, 16, or 17 degrees is not the point. In fact, what we're going to look at is how they converge over time, with what we have given as an evolution on the quantity of greenhouse gas in the atmosphere. So these models have improved over time. The first things they did was the grid size, because in fact they improve as the available computing power increases, basically. You know that traditionally weather organizations are among the buyers of supercomputers. People who like computers with very large power are people who do the weather. And with regard to the climate models, they run with an atmospheric part which is exactly that of the weather. So the grids are not as thin, but they are the same equations. The four acronyms, or the four letters that you have here, are representative of the first four IPCC assessment reports. So F for first assessment report, S for second, T for third, and since we already used F for first, we didn't reuse it for fourth, so we put AR4. Because we told ourselves that people may confuse them. It's not completely impossible. What you see are two things. First, the size of the grid has very clearly decreased. And the second thing you see is that topography has appeared. That is to say that initially the ground was flat. And in fact, what was differentiated was water and land. And on land, what you had vegetation and uncovered land that was differentiated. But it was not differentiated in terms of carbon cycle. It was mainly differentiated in terms of albedo. That is to say, the reflecting power of the surface. And then you see that over time, we make terrain appear. That is to say, we bring a capacity to differentiate in altitude what occupies a grid mesh, if it's atmosphere or if it's soil. We also have... yes? No, it's linked to the fact that on the first one you see it's flat. Yeah, indeed, there's a little thing on the right. If you want, let's say that... yes, indeed, on the left, there is topography. Oh, excuse me. But it is topography which remains very coarse. But you are correct. The second thing that happened with regards to the models is that over time they have become more complex with regard to the processes that are taken into account. So at the time of the first generation of models, let's say, they were mostly atmospheric, and the rest of the compartments of the planet did not appear. And so the exchanges with the ocean were parameterized, for example. That is, there was no ocean dynamics. The ocean was seen as an exchange surface with the planet, and exchanges were parameterized. And then, as generations of models improved, you start to have more and more compartments that appear. So you have an ocean, you have vegetation, the ocean starts to become dynamic, you have the aerosols, and now in the most recent models, you have most of what's going on in the atmosphere, or rather in the Earth to be more precise. Therefore, in the atmosphere and in the ocean. So you obviously see the clouds cover that appeared. Now there is atmospheric chemistry, you have a carbon cycle, etc. You have most of the major processes that are represented. Something interesting to note, by the way, is that the improvements of these models, not a single time has ever fundamentally changed the orders of magnitude of the temperature rise that results from the given increase in CO2 concentration in the atmosphere, quite simply because this rise in temperature results at the first order from the amount of extra energy that is sent to the ground by this additional greenhouse effect, and that comes from a quite well understood physical process of absorption re-emission by a gas, alright? And once you have the total amount of energy returning to the ground, and that you know how to split between what is absorbed by the ocean and what is absorbed by the ground, at first order you have quite easily your elevation in ground temperature. So the sophistication of the models makes it possible to better approach a certain number of local phenomena in particular. It makes it possible to improve the spatial resolution of what's going to happen. On the other hand, it does not change at first order, I insist, the global consequences, let's say, of what will happen, and in particular the average temperature rise, which represents the rise in quantity of energy contained in the system. The climate models, like all models when used by people who roughly know what they are doing, the first thing we do once we have developed them is to test them on the past. When you have a model, the first thing you do to verify that it works is to confront it to what happens before. And by the way, there's not a single economic model which passes this kind of exercise successfully, except if you change the parameters year after year to make sure that it sticks, but otherwise it doesn't work. As for the physical models, this is exactly how they are calibrated. And so this is exactly how we calibrate the climate models. What you see here is, and like in any IPCC chart, there is a lot of information. This is how a set of models, if I remember correctly, there are about 20 in there, how they compare with what has been observed with regard to the evolution of temperatures. So with regard to the evolution of temperatures, you have on each of these graphs, which represents either like an area, like here, or the whole world of emerged lands or oceans, like down here. Well, you have what the models tell you when we let them evolve with the change in greenhouse gases that has really been. That's the pink curve. You have in black what the real measurements of temperatures gave, you see, everywhere. And so what you see is that with a few anomalies at this time, for example, on the ocean, and so these anomalies are also on the global graph there. Well, you have something that models reproduce fairly well, the general trend on the variation of temperatures over the period. So the same modelers had fun looking at what the model, which reproduces what happened, would have given if the greenhouse gas emissions had not grown. And that gives you the blue curve. Well, more exactly, the blue envelope. So the blue envelope is the envelope of all simulations that are made in a climate model in a virtual world where man has not emitted any greenhouse gases. And at this point, you see that overall temperatures roughly remain constant. All right, the system is pretty much stable, whereas when you put the greenhouse gas emissions, the system drifts. There, so this kind of test is something absolutely essential to give credibility to these digital tools for what they will tell us for later. I do not bring it today, but you will find it on the internet for those of you who go look. Simulations, and in this case in real time, of these climate models which simulate the Earth as seen from the atmosphere. And so there is a comparison between real satellite images on one side and a representation with a digital model on the other. And when you compare the two, so take the test with someone in double blind, people usually can't tell which is which, all right? So today, there is also a quality of representation which is extremely good with regard to the ability of these models to visually represent the system. So we will talk about the future with these models once they have been able to retrace the past. What you have here is, again, a graph that is from the last big IPCC report. So, sorry, the penultimate, 2007, not 2013, but it didn't really change much in the last one. The interest of this graph is that it discriminates very precisely the way in which the temperature can evolve depending on the emission scenario. So that's the idea you need to have in mind. What you have here is the evolution of the temperature in the 20th century. You notice that the change in temperature over the 20th century is already a fraction of a degree that has been gained, and then the way in which the temperature evolves in the future according to the assumptions that are made on the greenhouse gas emissions. So the lowest assumption in these simulations is that the concentration remains constant, which means that basically the emissions start to decrease very, very quickly, starting tomorrow morning, and they become zero long before the end of a century. So there indeed you see that we can hold the 1.5 degrees. So there we have 1 degree, all right? We have started roughly from there, and so we hold the 1.5 degrees. Said differently, to hold the 1.5 degrees, emissions must start to decrease very quickly starting tomorrow and be zero long before the end of a century. That's what it means to hold the 1.5 degrees. And we're not off to a good start to do that. After that, you have here a scenario in which we keep constant emissions, basically, that's the scenario, And so what you see here is that this is a scenario in which we gain 2 degrees compared to 1990, which you have here, but we gain almost 3 compared to the pre-industrial era. All right? So what you have there is a scenario that's almost 3 degrees. What you see here is the envelope for this scenario of all the simulations, the envelope of all the models. In other words, the 20 models used with the same scenario, the more conservative tells you we will gain 1 degree compared to 1990, and the most pessimistic tells you we will gain 3 degrees compared to 1990. What this graph therefore tells you is that there is still a variability linked to the assumptions that are made in the model, because between all the models, you do not have exactly the same options that are taken for the representation of a certain number of processes, or more exactly for the values taken for the parameters or for the boundary conditions of a certain number of processes, because you have stuff that remains parameterized in there. So depending on the model, and because obviously the parameters, we try to adjust them, according to past observations. That's how we constantly try to recalibrate the model. So depending on the model that is used, you see that you still have an error bar, which is of the order of 2 degrees on this scenario, on the temperature increase that you have in the end. So we're not quite in the thickness of a line, because you will see that the consequences concerning or related to climate change are not at all the same at +1 and at +3 degrees. The intermediate scenario here is a scenario which is considered at least as a high-end coal scenario, at least in my lingo. That is, the emissions double. And you see there, still the same. What corresponds to this scenario is there. And so in this scenario here, there is a low version which goes to 1.5 and a high version which goes to over 4 degrees. So very often, there is a mistake made in the face of this kind of uncertainty, which is to say that if there is a great deal of uncertainty about the fact that we are in great danger, then I'll wait to find out more to be sure that really it is a great danger. So the parallel that I'm going to take is that if one of your buddies one day after drinking a lot asks you to cross the Champs-Élysées at 5 o'clock in the morning blindfolded, drunk, I think there's a great uncertainty on whether you're going to die or not. I'm not completely sure that you're going to do it. So in fact, a large uncertainty is representative, on the contrary, of a large risk. If there is a great uncertainty, it means that I am not able to give you an upper bound on what you risk. All right? So the idea that great uncertainty is a great insurance policy, which means that it is urgent to do nothing, is the exact opposite of a conclusion that must be drawn. Great uncertainty is great risk, a very big risk. And finally, my Polish scenario is a scenario, as you can see, that can take us beyond 6 degrees with a generation of models that was used at the time. So now we usually say that it's rather 5, but that doesn't really change much the conclusions that you get from it. So you understand, therefore, here that you have a dispersion, once again, linked to the model used for the same scenario. Another way of presenting the same thing is that when you do a simulation, in fact, we can also do a simulation. We can do things, in fact. We can, yes? No, it is compared to 1850. And so there is already 1 degree that has been gained. And so basically the emissions have to go to 0 tomorrow morning. So basically. So regarding how to understand that, I will show it to you in another way. For the same model, you can do several simulations with small parameter changes in the model. And of course, every time it'll give you a slightly different value. So you're going to have a distribution of results, and you consider that the value that you're going to keep is the top of the Gaussian if ever your results are distributed pretty much like a normal distribution. Or you can also consider that for a family of models, you will look at the top of the Gaussians for each of the models and take an average of all this and consider that this is what you're going to keep as the value of your multi-model simulation, what is called multi-ensemble among specialists. So in fact, what needs to be understood with all this talk about simulations, and it's another way of saying the exact same thing, is that when you are told for a given scenario of emissions, the warming that we obtain from it is so much, in fact, it should be understood that this so much is the most probable value of a distribution that looks like a Gaussian. So that's no way to guarantee that it cannot be more. Is that clear? This is no way to guarantee that it cannot be more. What is interesting with the rise in temperature that we are going to have, or what is essential more exactly, not only interesting, is to confront that to the past. Why? Imagine that I take a living being, and that I tell you, this living being, I will increase its temperature by 4 degrees. And I ask you, is it a problem or is it not a problem? Well, I'll tell you, it depends. If you take a goldfish, those of you who will ever have children, your children may one day claim a goldfish, and at this moment you'll find out that the goldfish needs to come along on vacation, etc. And so you are in a hurry for the goldfish to die, because that way you'll be freed from the hassle. So you can try to kill the goldfish to give it a little colder water, a little warmer water, etc. And then you'll see that the goldfish is doing like a charm, much to your despair. And why this? Because the goldfish is a cold-blooded animal. And so the goldfish, if you inflict a 4-degree temperature rise to the water in which it wanders, he doesn't give a damn. He continues to be there and well there, and you still have to live with his aquarium. If you inflict, therefore, on some animals a variation of their internal temperature of 4 degrees, that really doesn't bother them at all. So it doesn't matter. If I take a warm-blooded animal, like you for example, if I inflict a change of your internal temperature of 4 degrees, I just wait a bit and you're dead. So 4 degrees more, is it serious, doctor? For the climate system, the answer is exactly the same. It depends on the spontaneous variation of the system when it is left to itself. If we realize that the system on its own varies by 4 degrees from one week to the next, it really doesn't matter that the action of man causes a warming of 4 degrees, since it comes within the natural variability of the system. So it doesn't matter at all to do that. On the other hand, if the natural variability of a system is not of 4 degrees every other day, at this point, it gets very annoying, because it means that we inflict a destabilization that is unprecedented, and therefore there will be unprecedented consequences. So to answer the question regarding the climate system, we have to be able to reconstruct the way in which it has varied in the past. And so there is now a whole domain of science which is called paleoclimatology, which is used for that. That is to say, which is used to reconstruct the variations of the temperatures in the past. There are 2 main families of techniques for doing this, or 3 large families more exactly, and every time it's the science of a hole. We need to make holes. A first way to make holes is to make holes in trees, and if possible in very old trees, and like that we will measure the thickness and the hardness of the tree rings, which get aggregated year after year in the trunk. And so do you know how old the oldest living tree is today? 2000. Who says better? 700. Who says better? 4,000. So it's still a little more than that. It's 7,000. There's a pine in. So these are trees that generally live in areas that are in extreme conditions for life. So it's like snow in Antarctica. These are things that increase extremely little every year in a very slow metabolism. And I believe that it's a California pine in a semi-desertic area or something. So in this trunk we can make a hole, and so we have 7,000 years of climate archives. And so the problem is that we don't have global archives, we only have climate archives where the tree grows. And moreover, the tree does not grow in winter, so what does the archive give you? We are able with that to reconstruct the temperatures and the rainfall of the growing season, that is spring and summer. And from there, we already have a proxy to see how the climate system evolves as a whole over the year. The trees, you may have noticed, like me, that they don't grow much on water. So this method works well to reconstruct terrestrial temperatures. So as soon as you have access to trees or to fossilized tree trunks that you are able to date correctly, then you have access to a technique called dendrochronology, which allows you to reconstruct temperatures of the past. Once again, these temperatures of the past are reconstructed with a model, which makes it possible to go from observation data, the thickness and hardness of the tree rings, to an observed temperature, or an existing temperature more exactly. And you have the models that allow you to do that have, once again, a specific parameterization, so that every researcher who does this kind of thing, this kind of analysis, publishes his own results. And so you have here a compilation that has been published in the 2007 IPCC report, in which you have all the authors who are here who have each published a reconstruction of the temperatures of the northern hemisphere, because it is the most equipped, let's say, in land surface, during the last millennium. And so what you see over the last millennium is that there are 2 points of convergence in these analyses. The first is that everyone says that around the year 1000, more or less, it was a little warmer compared to the rest of the millennium. So this a little warmer around the year 1000 is known as the medieval optimum. So there is something that should interest you during the medieval optimum, is that there was wine in England, so because wine interests you very much. And in the other consequences that we had at that time, there is that the Vikings took out their advertising flyers and said, "Go to Greenland, it's all green." And in fact, Greenland, while it's very cold, it means green territory, right? So the story, which is a story which is often taken by the climate change deniers to say, look, the climate varies naturally, there was a time where Greenland was all green and so on. Obviously, Greenland was not all green. 1,000 years ago, there was the same ice cap than today over Greenland. On the other hand, you had a fringe of Greenland where you have no ice. This is, by the way, where some Inuit, Eskimos, and so on live. Well, you have some rocky banks. And so on these places where you didn't have any ice 1,000 years ago, like you don't have any today, the growing season of grass was a little longer than it is today. And so we suspect the Vikings of having gotten rid of a few people they no longer wanted to see by sending them there with herds, women, and children. Or you can read the story in Jared Diamond's book called Collapse. So there are a number of things which are questionable in this book, but I think, on the other hand, that this is pretty well told, and I think it's pretty correct. So we sent 5,000 Vikings there with their herds, and when the climate cooled down after the medieval optimum, well, you see that the growing season of grass declined, and so the cows died, and so did the Vikings, because they didn't want to start eating seal, and so they didn't like that culturally. And so the analyses converge to tell you that. You see that afterwards it cools down, and there you see that we are at something called the Little Ice Age in Europe. The canals in Bruges freeze completely in the winter. We're freezing to death. The Marquise of Sévigné lights a fire in August. In short, it's crazy. And it's, by the way, at that moment that the French Revolution takes place. And you know that the French Revolution was born after a great famine that took place in France that killed between 500,000 and 1 million people, all right? And so it is a time when the harvests are not good. So it triggers trouble, because people don't like to have an empty stomach. What you also see in the third convergence of all these things is that from the beginning of the industrial era, crack, all of the analyses tell you that it starts to go up quickly. So the first conclusion that we can draw from this analysis on the scale of the millennium is that we are already here in a temperature shift which is totally out of trend and which is going much faster than any trend that you can see. So I'm talking about trends, not annual variations, but the trends that you can actually identify from this. So afterwards, we can go back further in time. So I'll show you later, but we can go back there on this graph up to 60 million years. And so if we look at 60 million years, what we see is that since this time, well, and so be careful, the present is here on the left and the past is there on the right. We see that what happened is overall a slow cooling of the climate system. And this slow cooling of the climate system has particularly gone with a significant decrease in the quantity of CO2 in the atmosphere. So over very, very long timescales, indeed, the climate has tended to rather cool down. What you also see is that a long time ago, the climate has been almost 10 degrees warmer than today. So the fact that the climate is warmer than today is not necessarily something that is a first in the planetary history. On the other hand, what is a first in the planetary history is that, and what we're going to detail on from now on, is a variation of this magnitude applied to a sedentary humanity of 7 or 10 billion good men. All right, that's new. And if there have been large-scale variations in the past, at no time, at least as far as we are concerned, have they prevented our species from developing since we are here. On the other hand, between not harming the species and not harming any representative of the species, there's a small difference. In other words, if the current climate change leaves only 5 million good men alive, this is more than enough to ensure the perpetuation of the species. It does not pose a problem for perpetuation of a species. So the subject that we will see from now on is not so much, is mankind going to go through, and I can already give you the answer to that, which is yes. It is, can we have an idea in which conditions and how many of them? And these are questions that remain unanswered. So I will now introduce a more recent temperature variation than the one that happened 65 million years ago with this little map, which represents, or rather two maps that represent Europe. Here you have a schematic representation of ecosystems, which are therefore the reflection of a climate system, because the reflection of a climate system is the installed ecosystems. The ecosystems installed in Europe today, if we do not remove them to make, well, essentially fields, but also roads, factories, bridges, railroad tracks, and this university, well, if we do not remove ecosystems to do that, we have in Europe essentially forests. This means that the climate is humid enough for large plant species to grow, and that, moreover, it is neither too cold nor too hot, so that the metabolism of these species is not hampered. This is what Europe looked like 20,000 years ago. So 20,000 years ago, in the evolution of the Quaternary, we are at the heart of the last ice age, and so it's much colder than today, otherwise it wouldn't be an ice age. Soon you'll see by how much. And as it is much colder than today, the landscape of the planet is not at all the same, and the landscape of Europe is not at all the same. The first thing that you can see is that you can forget about Erasmus in Sweden, since there are no Swedes, there are no Danes, there are no Finns, and there aren't even any North Germans, and there are no Scotsmen. So that's good for the rugby players. But so all of these people, these good people, are under ice. So you have a huge 3-kilometer thick ice cap that covers the whole of Scandinavia. So for those of you who like them, there are no Quebecers either, since the whole of Canada is also under the ice, so there are no oil sands, good news. You have a huge ice cap, even bigger than the one on Scandinavia, which lies on Canada. This ice is made up of water, the young engineers bet you are novice, and this water had to be taken from somewhere. So there is clearly not enough water in neither the lakes, nor in the rivers, nor in the atmosphere to make this much ice. So the only place where you can take this much water to make this much ice is the sea. And since the sea is a big bathtub whose bottom has not changed, well, if you take water to make all this ice, the water level drops, and the water level is lower by 120 meters.
So there's also no index sailing cup since there's no channel.
So you forget the sponsorship to go sailing, and you can finally take care of serious problems. Just joking. So the low point of a channel today is 114 meters, and since the water level is lower by 120, there's no more channel. So for those of you who have heard of it, you can also go into the Kosker Caves on dry ground. I don't know if you know where the Kosker Cave is. Well, the Kosker Cave is a cave whose entrance is now submerged, and which is found in the Mediterranean. So it means that you have to go down 30 meters below the water level to enter the cave, and inside you have an ascending shaft, and the cave is preserved with the paintings, etc., like in Lascaux. And this cave today, its entrance is submerged, and it means that at the time it was inhabited, one could enter in dry land, because obviously prehistoric men did not have autonomous diving suits, and so the water level was much lower. The climate was much colder, so there was much less evaporation, and so it was much drier. And in this much colder and drier climate, the vegetation installed in Europe looked more like what we have today in northern Siberia.
So it's not very luxuriant, okay?
The shimmering wheat fields of nowadays and the shimmering forest of Fontainebleau are not really there. And in this kind of ecosystem, we managed to support 100,000 good men, that is to say 100,000 animals at the end of the food chain, and it's roughly the human population of the time. So you see, it's not even the number of students in prep classes. I think, well, it surely is not the number of students in high engineering schools, period. So you see, it's a small staff, the French population of the time. So on the left, Europe in the Ice Age. On the right, today's Europe. So I repeat, when you go from the landscape on the left to the landscape on the right, you have a global warming. Do we agree? Well, this warming, historically, is 5 degrees in 5 to 10,000 years. It's just that. So we have a historical precedent to a few degrees of heating in absolute value, and you see the kind of thing that it produces with regards to the landscape. So another way to put it is that the natural variability of the system is not at all on the scale of what we are triggering today, all right? So the correct parallel is not the goldfish that will resist to anything. It is indeed you who cannot resist to a variation of a few degrees of your internal temperature as long as I impose it long enough. All right? This is the correct parallel. So if I put into perspective now what happened over the last millennium, what happened over the last century, and what could happen in the future, this is what it looks like. Here you have a reconstruction from the dendrochronology, like I was saying earlier, essentially the temperature of the past century. So that is essentially done with analyses. Starting 1860, you have, let me comment that. You have a direct measurement of the temperature rise of the planet. And so question, why didn't we do this before 1860? Why not before 1860? No. Much simpler than that. And in particular, with what do you measure a temperature? With a thermometer. When was the invention of a thermometer? No. 1492. Except that in 1492 you have one thermometer, and do you measure the temperature anywhere on the globe with one thermometer? No, it's a little complicated. So you need many thermometers to start measuring the temperature at all points of the globe. Moreover, what is the Earth's surface mostly made of? Of water. Do you have a lot of cities and a lot of fields on the surface of the ocean? Not a lot. And do you have large populations and a lot of thermometers on the ocean surface? No. You still have thermometers on the ocean surface. Where? Sorry? On boats, absolutely. So since you have engines and steam engines, you have in particular thermometers at the water inlet to measure the water temperature, because this is used to adjust the machines. And even then it did happen that we took some samples, etc. So, except that these samples are only made on trade routes, because boats go around to transport goods. If they start going sightseeing, their bosses yell at them. And so you have to wait until we have enough trade routes on the surface of a planet so that we consider that the measured temperatures in the ocean are representative of the water temperature. And therefore, to have enough thermometers on land surface and enough thermometers on boats that move around to consider that we have something which begins to look like a representative sample, we consider that before 1860 this is not the case. So starting 1860, we are able to offer an instrumental measure of the planetary average. Yes? No. It is representative of the temperature of the water where you pass. It's not the wake of a boat, it's not the drag of the boat that will heat up the water to the point that it disturbs the measurement. Definitely not. And so you have in perspective here, I repeat, 3 temperatures measured in different ways and at different times. So their analyses, they're instrumental, directly with thermometers, and they're modeled. So there, no more thermometers, we go to modeling, and it's modeling of what will happen later. And what you see without the hint of of, let's say, without a possible discussion on this graph is that the coming temperature variation is something that is without commonality, whatever the scenario adopted, with the natural variability of the system. So even at 2 degrees, that's the consequence, well, the conclusion that must be kept in mind. Even at 2 degrees, we will see a considerable amount of malfunctions in the system that did not exist until now, even at 2 degrees. All right? If we, well, in fact, here is the curve which gives you the variation of the system on timescales, well, let's say since the last ice age maximum. So here you have the reconstruction of the temperature of the past with analyses. So when you are at the scale of the tens of thousands of years, it is no longer the rings of trees that we use, it is the reconstruction with the isotopes of oxygen and hydrogen in the ice caps. So this is what I talked about last time. So you see here that the temperature at the start of the Holocene was slightly greater than what was behind it. That is what we have already done today, and that, with the correct scale, is what we could do in the coming century. So you see that obviously the image of the wall is quite good. A rise of a few degrees in a century looks more like a wall than a walk in the park. It's really going to cause major malfunctions all around the system, and we will get into more detail afterwards. Something that is important to keep in mind is that this temperature rise already underway, and which will accelerate from time to time, it will... Yes? Yes? To be exact, the solar radiation is rather 230 watts per square meter, and the greenhouse effect is more like 170, but it's that order of magnitude, yes? The additional is 2.5 watts per square meters. Yes, ma'am, that is enough. Well, first, it's 2.5 today, and I point out that it increases over time. And for example, we will see a little later that what we call RPC, representative concentration pathways. In fact, the number that you have after it represents the radiative forcing in 2100. So the RCP 4.5 is 4.5 watts per square meters in 2100. So they increase in simulations, obviously, over time. And moreover, it must be seen that in order of magnitude, and it really is an order of magnitude, 1% increase of the greenhouse effect is 1 degree more, basically. So 4% increase is roughly 4 degrees, basically, and I do say basically because the process is not at all linear, and these are the orders of magnitude. So I was saying, the rising ground temperature, so from time to time it takes a little break. This little break does not call into question what is happening, so quite simply because there is a little optical illusion in this story. A lot of people consider that what is representative of what is happening at the moment is the rise in temperature of the atmosphere. So in fact, the rise of atmospheric temperature is the tip of the iceberg, because what this diagram shows you is where the supplement of energy that comes from these supplements in greenhouse effect is going. And this extra energy, what you see in this picture, is that over 90% is not heating up the atmosphere, but the ocean. It's the ocean, and I told you this before, that controls the inertia of the system on the timescale which interests us here. However, it is sufficient that the switch, which distributes the energy between the ocean and the atmosphere, changes a little in a given year. For example, you have the circulation that buries the heat in the ocean. It suffices that it is a little more active, or on the contrary, a little weaker, and at this moment you will have either an acceleration of the surface temperature rise, or on the contrary, a slowing of the rise, or even a slight cooling of the surface temperature in a given year. The variability of the atmospheric temperature depends in particular on this heat burial process in the ocean, which can experience small variations due to small variations in the ocean circulation. It doesn't preclude the fact that overall, the system accumulates more and more energy. But if this energy is in an intermediate layer of the ocean, for example, you don't see the translation in surface temperature. Yes? How does the exchange of energy take place? We'll see that later. It depends on the large-scale oceanic circulation. So you have a convective process in the ocean, and when the water that was on the surface goes deep, it takes with it the heat, all right? And it is replaced on the surface with slightly colder water that comes from the depths. And it suffices that this movement accelerates or decelerates a bit, and basically have a process of bearing the heat from the surface to the depths, which accelerates or, on the contrary, slows down a little. And so that is an element that steers the surface temperature. So we will now begin to look at the impacts in a little more detail. There are two things to keep in mind. So one, I repeat, the magnitude of the impacts depends on the magnitude of the emissions. So everything I will tell you about from now on is qualitative, semi-quantified for a number of consequences. There are people who ran models saying, if the emissions are higher, such an impact, we're able to put it in such a range, whereas if the emissions are lower, such an impact, we would rather put it in such a range. But it will depend, basically. And above all, the essential point is the last sentence, that is to say that what I show you from now on is illustrative. These are things about which we already have indications. There are lots of things we're going to learn as we go. That is to say that we will realize, once it's too late, that there is this thing, that blow that we had not seen coming, and that is starting to build up momentum, all right? And that there will be more and more. And we'll have to live with it. There's going to be more and more because the system is way too complex, too chaotic, and too strongly non-linear for us to be able to identify risk by risk, geography by geography, and date by date what could happen, all right? And that will forever remain impossible. So a joke that I often make is, you see there's an experiment that we did 3 billion times or 4 billion times or 5 billion times with humans, and it's called getting married.
And with all that, a couple who gets married today, you don't have any idea where it will be in 30 years.
So imagine an experiment that we are doing for the first time, which is as complex as this one. It is completely delusional to claim to say in advance all the consequences that it will have in a few decades. All right, so we can have an idea, just like with the couple. I don't know in 30 years if they will still be married or not, but they will still have 2 arms and 2 legs. Well, unless they had an accident, but they won't have 4, for example. They won't be 3 meters high. So there are a number of things that we are always able to say, and there are a few things that we are absolutely unable of saying. I don't know if they will have 2, 3, 0, or 5 children, or whether they will still be together, or where they will live. So for the climate, it's exactly the same thing, or more exactly, it's worse, since once again, it is an experiment that we are doing for the first time. And experiments that we are doing for the first time, it's very, very rare that it gives exactly results that we can predict in advance everywhere and all the time. Once I said that,
there are a number of constants in this story.
The first is that warming will have a spatial structure which is already more or less known. The first that you see is that the temperature, so here for instance you have it in June, July and August, and here in December, January and February. You see that whatever the season, the rise in temperature is more pronounced on the land surface than it is on the oceans, because the oceans have more thermal inertia. The second thing you see is that the temperature rise is proportionally more pronounced in winter in high northern latitudes than in summer in high northern latitudes. In other words, the rise of temperature will go faster in winter than in summer. That's what I told you last time. What you also see is that in all cases, there is one place, and I will come back to this later, I will explain to you why, where the rise of temperature is less pronounced than elsewhere in the northern hemisphere. It is the immediate south of Greenland. All right, you notice that it is present whether it be in summer or winter. So the first of the consequences that you will see here is that if there is one place where it will particularly heat up. It is in the Arctic region. And for those of you who follow the news a bit, you may have already noticed that it is in the Arctic region that from time to time there are totally mind-blowing temperatures, and the word is not too strong, during winter. I believe it was on January 1st, 2018, if I remember correctly, that the temperature of the North Pole was positive. I repeat, positive, above zero. All right? So, the second thing is that, so as I told you earlier, the temperature rise will depend on the emission scenario. So here you you see the acronym appear, RCP. So I say it again, representative concentration pathway. So the 2.6 is a scenario where the radiative forcing is in 2100 is 2.6 watts per square meters, which is approximately what we already have today, basically. The 4.5 is that we have 4.5, and the 6 is that we have 6 watts. I purposely removed for you here the highest of the 4 RCP scenarios used today, which is called the 8.5. So I took it away from you. It's a manipulation that I assume. I took it out because this scenario with very high RCP corresponds to very high emissions. That is to say, a situation which for me is totally virtual, in which humanity would be better and better off, and there would be more and more men with an increasingly important economy, even as climate change is at its maximum possible consequences, and so you have the planet that is starving to death. So it's a bit complicated for me to put the two together, so I considered that this one I would speak little of it. And from time to time you will see it anyways, but I will talk about it very little. Because it has an internal inconsistency, which is unrelated to physicists, I insist, which is linked to the fact that the scenarios that are made by the economists, who do not have the physical limits in mind by construction, this is what I explained to you in the first course, as long as the economy does not depend on limiting factors that come from physics, there is no reason why we can't have an economy which is extremely important with the very limited physics. And it's not a problem for them, but it is a problem for me. Yes? No, not at all. It is only the internal dynamics of the model. It is the fact that you have between the models, again, assumptions. I'm going to give you one example, which is very well known. The parameterization of clouds. So I told you earlier that in the standard model, you have a grid size of 50 to 100 kilometers. For all of you who have once daydreamed in summer lying in the grass observing the clouds, you will have noticed that the clouds do not cover 100 kilometers. All right, there aren't many clouds that go from here to Chartres, and that you could see all at once, by the way. Or it's called a stratus blanket, and it's depressing and it's winter. And so the cloud is a phenomena under the mesh. So to take into account the cloud cover in the models, you're forced to parameterize this cover. In other words, what your model will simulate is the circulation of water vapor in the atmosphere, and depending on the water vapor that you have in your mesh, in your shoebox, well, you will parameterize, and this isn't a dynamic thing, it's a parameterized thing, the quantity of clouds that you have in this mesh. All right? Well, depending on the techniques that are used by the different modelers to make this parameterization, the quantity of clouds that you have for a same water vapor concentration, and the fact whether these clouds are low altitude or high altitude clouds, which do not have the same impact on the climate, well, this will vary from one model to the other. And this parameterization alone explains most of the dispersion of results between models. All right, the bulk of the dispersion of results between models is how the models approach the representation of clouds. So here is an example, which is the most emblematic example, and it has absolutely nothing to do with the climate feedback on the economy, since I told you that it is not taken into account by construction in any simulation. So what I was saying is that depending on the intensification of the greenhouse effect, let's say, you have warmings which are more or less pronounced, but you find these constants each time. That is to say that it warms proportionally more on the continents than on the oceans, more in the northern than the southern hemisphere, and that you still have this singularity just south of Greenland. Yes? This is the increase in radiative forcing. It is the increase in greenhouse gas concentration in the atmosphere and hence the radiative forcing. So this is the name of a scenario, and the value you have after RCP gives you the radiative forcing in 2100. This being the case, for a same value of RCP in 2100, you can have multiple trajectories. So it's one trajectory, and I could have shown them to you, but this is one trajectory. I prefer to stay with my emissions scenario story because it pretty much overlaps. And the emissions scenario is something that is much easier to visualize because it's the quantity that we emit. Variability, that is to say, of models? The forcing is not variable here. The 2.6 is a defined forcing trajectory. On the other hand, having 20 models gives you a dispersion of the results because you have one result per model, but these are all the same RCP scenarios. Afterwards, the same models, you can use them with an RCP 2.6, an RCP 4.5, etc. And at this point, obviously, they don't give you the same results. No. It is compared to the pre-industrial era. That is to say, it is 2.5 due to man. And indeed, the pre-industrial reference due to man, it's 0. Yes? So there, if anyone is able to give me a reliable forecast of where the migrants will be in this kind of evolution, I pay him like cherries. I'm not taking any risks because it's starting to be the season. Typically, this is part of the end of chain consequences, which are unpredictable things. What you can manage to predict is the pressure factors that are going to cause that sort of thing. But after that, I personally can't tell you if people will first migrate or first die because of an epidemic. So if there's are epidemics, they will not migrate because they will be dead. So I don't know. The answer to this question, I will come to it at the end of a presentation on consequences, because that's the first thing that comes to the mind of a journalist, but that's the last thing that comes to the mind of a scientist when it does come to his mind, because precisely it is very difficult to be predictive on this kind of stuff. It must be understood that the further we move away from physics and the more we move into things that affect us, because once again, we don't live in a world of temperatures, we live in a world of men, whether there are things to eat or not, whether there are animals or not, and whether our neighbors come to our house or not. This is the world in which we live. And so the physicist, he loves the world of physical parameters, and he wants to stay in this world and not to venture too much around into things that are... Well, every time we venture into consequences that are closer to us, let's say, we add a layer of complexity to the reasoning and therefore a layer of uncertainty. So it doesn't mean that the risk isn't there, it just means that it's difficult to formalize it. I'll come back to that later. So, I told you that since 1860 we have observation data on the temperature variations. Here is a translation of that, and in this case it's since 1880, but whatever. What you see is that since basically the post-war glorious 30 years, there has been a very characteristic rise of the temperatures, and even before. During this period, when the temperatures has temporarily gone back down, one of the hypotheses that holds up, and I do say one of the hypotheses that holds up, is that this phase, which corresponds to the beginning of the so-called glorious 30 years, and therefore to the beginning of the accelerated industrialization of mankind, has gone hand in hand with a big emission of sulfur dioxide into the atmosphere, because we used a lot of oil, more and more oil and coal, which are sulfur fuels, and therefore there were not any anti-pollution measures like we have today, and so we didn't purify sulfur dioxide from fumes. So we put a lot of sulfates in the atmosphere, and so it cooled the climate a bit because of that. That's the explanation that, one of the explanations that holds up. Because you notice that if you start from here, and that you go to, and that there's the same trend with a peak there, which continues after, and then there's an acceleration. What you also see is that here the trend is very clear. So that doesn't prevent a number of people still today to take a shorter time series that suits them and say, look, the temperature is dropping. It stopped rising since the temperature is dropping. All right? Well, obviously, you have to take the long time series. So you have to apply the right filter, and you shouldn't watch short time series. So you'll tell me there are fewer and fewer climate skeptics. Well, this is not completely certain. It depends a lot on the country where you are. And it turns out that there is one country which is, no longer the first, but the second emitter of greenhouse gases in the world. which has a very small influence on the rest of the Western countries because it currently holds their reserve currency of choice, which is called the dollar. And this country has the highest proportion of climate skeptics in the world after Saudi Arabia and I don't remember which is the second. So there. So yes, it's about 20%. And people who who are quite strongly skeptic, let's say, not and with the same measure in France, it's 6%. All right, so oh no, not 20, it's 15. Sorry, but with the same measure in France, it's 6, so it's roughly twice as much as France. So, and it is very differentiated according to the geographic region, and so this little animation, once again, is there to remind you that it is very easy to manipulate statistics to make them say what they do not say. And here you have a particularly classical example, let's say, of this kind of manipulation. There is not only the global temperature that we can analyze with temperature readings. So here you have an evolution of the hemispherical temperature, and you see, for example, that the temperature variations of the southern hemisphere are overall a little less impacted and a little slower now than the variations of the northern hemisphere. This is the consequence of what I told you earlier: more continents in the northern hemisphere and a faster evolution in the Arctic. Here you also have differentiated averages between continents and oceans. So we find the conclusion that I told you earlier. Above the continents, you see here this decrease, probably due to the increasing industrialization. And there you see that now it evolves more slowly than above the continents, which is quite normal with the differences in thermal inertia. Here you have the curve for France. So you see that France today has temperature anomalies compared to 1961-1990 average, which are now all positive and which in trend are increasing. So that, for example, throughout your life, you will see in the newspaper, as long as we have newspapers at regular intervals, we have just broken the temperature record. Yes, well, we'll break them again and again and again and again and again. As long as there are people to measure temperature and newspapers to print stuff on temperature, we'll periodically break the temperature records. Yes? Sorry? Well, we don't care. We take any reference. I mean, to characterize a variation, you put the zero of the ordinates wherever you want. And here, in this case, the average is not over 100, but over 30 years. So, on the other hand, what is certain is that as far as climate is concerned, we tend to consider the minimum time series to watch what happens somewhere is 30 years. All right? Usually, yeah. Here you have a variation of winter and summer temperatures in France, there too, for a century. And so what you see, and that's an interesting thing to keep in mind, notably for the sizing of the electrical grid, which is that the variation of temperature with respect to winter, which is the same as with respect to summer, that is to say that it increases in all cases, well, it does not eclipse the annual variability, which tends to be more important than with regard to summer. So here you have a point which is extremely singular, you see, otherwise the temperature anomalies are still very similar from one year to the next. While there, the temperature anomalies from one year to the next, they can vary much more. And so what this graph is telling you in particular is that global warming as a whole will not, or does not prevent, to be more precise, today, the occurrence from time to time of winters which can be cooler than average. All right, it does not prevent that. It will be obviously less and less frequent, but it will not prevent it. You now have, yes? The seasonal normal is always the same. It is the average over 30 years of 61-90. But once again, it's just a matter of moving the origin. One of the ways to find out if what has already happened as warming of the surface of a planet is indeed due to an additional greenhouse effect, it is of course to see if the model gives you a temperature rise on the ground that is consistent with the additional greenhouse effect that has been put into the atmosphere. But another way to have this confirmation is to see if the spatial structure of the temperature rise corresponds to what we are in right to expect from a climate that warms with an additional greenhouse effect. And I think I said it once before, but if not, I'm going to repeat. In a climate which is heating up by additional greenhouse effect, one of the things that one should expect is to find a temperature rise more pronounced on the continents and particularly pronounced in the Arctic zone. And here you have a reconstruction of the temperature variation over the 20th century. And what you see is that this is what we observe today in the temperature elevation that is already observable. So you see that it is particularly pronounced in the Arctic zone, and that it is more particularly pronounced in the continents than on the oceans, where it has warmed up. And you also see, and again I'll come back to this later, that we indeed have this singularity here just south of Greenland. One of the consequences of warming temperatures is that, obviously, we will have an increase in the maximum temperatures. As long as the temperatures obey a distribution, if you do not change the shape of a distribution and that you move the average, you'll obviously, you will see events appear which exceed the maximum temperature that you had before. See, if the maximum temperature was there and that you move the average, the maximum temperatures reached will be there. Now, as long as you don't change the shape of a Gaussian, well, the probability density, let's say, of the events that exceed the old maximum temperatures are not extremely important. On the other hand, if at the same time you increase the variability, then you will see a much larger increase in events that will exceed the old maximum. But it turns out that, unfortunately, one expects in a climate which heats up that the variability also increases. All right? This is one of the consequences that is expected. This means that extremely hot events or extremely dry will tend to increase faster, let's say, than the average. There is another element of variability that can come into play. And here I will give you the example of Europe. Europe, as you know, is subject to a westerly wind regime. It turns out that over the Atlantic, you have four regimes of respective positioning of the depression and the anticyclone, which can occur. You have a regime, this one, called the NAO-, in which you have the high pressure anticyclone in the north and the low pressure depression in the south. You have here a regime in which it is the exact opposite. You have here a regime in which it is an east-west structuring, and here a regime in which it is an inverse east-west structuring. Here you have the frequency of occurrence of these situations in the year, all right? So yeah, year by year. So what these graphs tell you is that with a strong annual variability, come on, well, basically over a few decades, you have roughly 25% probability of finding yourself in one of these four situations. In other words, if you look over a few decades and you ignore the annual variability, this happens 25% of the time, this 25, this 25, this 25. And when you are in each of these four situations, you see here that the temperature and precipitations have anomalies compared to the average, which are not the same. So when you are in red, then you have a surplus, and in blue, then you have a deficit. So watch out for the temperatures and precipitation. It is not interpreted in the same way, obviously. And you see that the surplus and the deficit are not at all located in the same place, depending on the situation that you have in the Atlantic. So here, when inverting the North Atlantic oscillation, well, you see that the surpluses and the deficits are roughly reversed in the northern part of Europe. There it's the same. By inverting these two situations, well, you see that on the northern part of Europe, you have extremely contrasted situations with regards to precipitation.
One of the questions that modelers don't know how to answer still today is,
does the frequency of occurrence of each of these four situations change in a warming climate? If the answer is yes, it means that we have an amplification process in Europe compared to the global evolution, either in one way or the other. If the amplification situation is in the direction of less precipitation and more temperature, we are much worse off than if it goes the other way. And I insist, much worse off, because you have a direct impact on what is eaten and a direct impact on what grows. And it's very difficult today to know anything about it with models. So application, here you have the temperature distribution in Switzerland. So don't ask me why Switzerland, it's probably because it was a team of Swiss researchers who did this. So in the pre-industrial situation, I'm talking nonsense.
So here is the average of the end of the 20th century,
and here the future climate in the late 21st century. What you see is that
not only has the average of a temperature distribution changed,
but you also see that the variability has considerably increased. And so the extremely high temperatures are not going to be a little more frequent, they will be considerably more frequent. So you are perhaps a little young to remember the heat wave of 2003, because it was nonetheless 16 years ago. 16 years ago you weren't tall. I don't know who does remember the heat wave of 2003. All right, not bad. Well, the heat wave of 2003, what I'm going to tell you is that in a climate that heats up a few degrees, so that's what we're set out to achieve, well, that becomes the normal summer. So the normal summer is the normal summer in the statistical sense, that is to say that it is the summer which separates 50% of the coolest summers from 50% of the hottest summers. This therefore means that by the end of a century, with a warming of a few degrees, 50% of summers will be warmer than summer 2003. Therefore, so in the consequences that you can easily imagine, you can say goodbye to forests, we can say goodbye to a part of the harvest, etc. It's quite easy to understand that all this disappears. So this is to make it clear that a variation of a few degrees of a planetary average, that is not at all representative of the upper limit of the temperature supplement that will take in the most severe hot events. It is not at all representative of that.
Other consequences
of global warming at ground level, which are expected, I told you about it last time when talking about the physical process at work. That is to say, from the fact that by intercepting the temperature closer to the ground, we were going to have less that would be intercepted in the upper atmosphere. Well, we must expect to have a cooling of the stratosphere. What you see on this graph is that since we know how to measure the temperature in the stratosphere, that is to say, since the start of probe balloons, well, we can measure the temperature in the stratosphere, and what we observe is that it goes down. And it goes down in a way that makes sense with the additional greenhouse effect. The second consequence that there will be with global warming, or more exactly with climate change, it is a variation of precipitation. So what I told you last time when I simulated the overall workings of a system for you with the little animation I showed you, is that in a warmer climate, you generally have more evaporation and therefore more precipitation. On the other hand, this precipitation has no reason to evenly distribute on the surface of the planet, neither spatially nor temporarily. And so the big question is, what is happening to the evolution of these precipitations? There is a modeling difficulty, which is linked to what I mentioned earlier about clouds, which is that since precipitations are linked to the cloud cover, well, if you have trouble parameterizing the cloud cover, we have an uncertainty which is greater than on the temperature rise on the variation of precipitations. Nevertheless, we will still have some robust conclusions. So what you see is that overall, the precipitations are going to have a tendency to increase sharply in the high northern latitudes, so that only half interests you because there aren't many people that live there. However, what you see is that there are regions where precipitations will tend to decrease. So if you look at this map a bit macroscopically, what you see is that the precipitations increase at high latitudes as well as globally in the equatorial band. And I do say the equatorial band. On the other hand, they will tend to decrease. They will tend to decrease sharply in the tropical bands that you see here and here. And the region of the world where precipitations will decrease the most, no luck, is where we live. You see that where the precipitations will decrease the most among all regions of the world, it is around the Mediterranean basin, and the rim of the Mediterranean basin has notably a number of countries here that are not at all self-sufficient in terms of food, and who today need to import food for a rapidly growing population. And actually, I don't have the time today, but I did a lecture at Physique Chimie Paris University 4 years ago, whose title was From Daesh to COP21, in which I explained how what has been called the Arab Spring had an extremely important energy-climate determinant. And in fact, what happened there were food riots in importing countries that were not able to subsidize their imports for their population. And so the exact same thing as in 1789 happened, that is to say, riots. And Syria has a triggering process which is not very, very far from that. This kind of stuff is going to repeat itself, all right? Seeing how things are going, this kind of stuff will repeat itself simply because precipitations will continue to weaken around the Mediterranean basin, and therefore it will make it even more difficult to have food self-sufficiency in these countries. And besides, I'll take your question later, and besides, the drought will unfortunately tend to go up towards the south of Europe. And you might know that already today, Spain has an agriculture which is partly fed by pumping of aquifers which do not replenish themselves. So it's a problem that will very much concern Europeans on their own soil as well in not that long. So when the IPCC presents this kind of stuff, it's an intermodal trend over around 20 models. And so this, unfortunately, is a very robust conclusion. That is to say that all the models converge on the fact that the rim of the Mediterranean basin will dry up. You have places, those colored in white, where you have no convergence between models. All right, typically. There, it is unfortunately very, very convergent. So afterwards, you don't just have the precipitations that matter. You also have a variation of evaporation because the water content of the soil, which conditions whether plants will grow or not, is the result of what falls minus the result of what evaporates or slips away quickly. For example, in monsoon areas, where rain is also something that is absolutely crucial for people to survive, well, you may have precipitations that intensify, but that come after a dry season which was drier, therefore the soil is more impermeable, and at this time the water trickles over the ground, which causes flood, by the way, but is not preserved by the soil, so which is not good, let's say, for vegetation. The ideal for vegetation, for those of you who have been to Ireland or Brittany, it's the little demoralizing drizzle all year round. That's absolutely perfect. It's when the weather is good 3 times a day, as the Irish saying goes. So that's ideal. But when you have episodes that are very concentrated, unfortunately, it's not very good either. So what you see here is evaporation. And be careful, because the graduation is that the more blue it is, the more it increases. And you see that in a number of regions of the world, and in particular over most of the emerged lands, evaporation goes from somewhere between the same as today to more intense than today. So in any case, even if it rains more, you are going to have an evaporation, in particular over land, which will tend to intensify. And so here you have something which is a composite of what I just mentioned, so precipitation and evaporation, which is the evolution of soil humidity. So that, in fact, it directly controls the agricultural yield, basically, and whether ecosystems are doing well or not. What you see here is that we are going to find things that I have already mentioned. So the periphery of the Mediterranean basin tends to dry up there. Where you have dots is where the conclusions are very robust. That's the, okay, I'm just finishing to comment and I'll take your question right after. So this is how you understand this graph. You also see that part of Australia there, the southwest quarter, which is drying up a little, and the southeast corner as well. And this is where you have, for those who follow, sometimes farmers that are not very happy with what is happening. You may have heard already about the water problems in South Africa, and you see that it is consistent with the map here. And so that is the very bad news. If you have the Amazon basin that dries up, this is something which is absolutely not going to be good at all for the forest, because there you have the largest stock of standing carbon on the planet, and you also see the intensifying drought over the southern United States and over Mexico. So Mexico is like North Africa, growing population, intensification of droughts, and therefore an availability of water. So it's the same. The question of how it's going to end is a big question mark. As I was saying earlier, oh, my bad, there was a question at the back? Yes? Oh, so no, because water vapor condenses. In fact, what you have in the atmosphere is saturating vapor pressure, and if you evaporate more, it rains more. It does not increase the saturating vapor pressure. It circulates faster, basically.
What conditions the saturating vapor pressure is the temperature of the atmosphere.
So the higher the temperature is, the greater its capacity to transport, or the concentration of water vapor in the atmosphere is, basically. The more humid it is, the greater its ability to be humid. Yes? Yes, it would negatively influence the economy, except that they don't take it into account. Yes, that would buffer the emissions. It would dampen them. It would lower them. But they don't take it into account. It's very complicated because, again, here you start to touch on the complexity of the thing, because here we are still in physical parameters. Afterwards, for example, when we start doing agronomic simulations, with the evolution of these physical parameters, we add a level of complexity. So you have to go ask your friends in agronomy. Well, they're still here
for the moment, but they'll soon go to the Saclay campus like everyone else.
Well, you have to go ask them, and don't laugh, that might be you one day. No, just kidding. So you need to go ask them how it works when you add the biology of a plant on top of the evolution of these physical parameters, and the answer is that it's complicated, as you'll see a little later.
But you don't eat physical parameters, you eat plants.
And the animals who ate the plants. So what this graph gives you is the evolution of intense rainfall phenomena as they have been observed, so this time in the past. And what you see is that there is already an increase in the trends, so where it's green and blue, in a number of places. So the excess precipitation can come in the form, unfortunately, of an increase in precipitation over extremely short periods of time, and that is just lost for everyone because it is water that the soils don't keep, and in addition it causes damage. What you see here, and in this case it's also the past evolution of the soil drought index, and you see that there are a number of regions in the world where we find the trends that are planned for the future. So there, since it's in the middle of the Sahara, it's not very significant, but you see that on South Africa we find that, on the Mediterranean rim we find this, on the southeast and southwest of Australia we find this, on this part of Brazil we find that, and on the southern United States we find that. So there are already a few regions of the world where it would seem that we already have soils that are drying up, like we expect to have in the context of a warming climate. In France, you have an intense precipitation phenomena called Sevenol episodes. Have you heard of it? No? So Sevenol episodes happen at the end of the summer, when the Mediterranean is still warm, and where the temperature on land has begun to cool down, And they happen when you have humid air from the south that has passed over the Mediterranean, so loaded with water, that rises in altitude. So with condensation of water vapor when meeting the Cevennes, that is to say when meeting
The foothills of the Massif Central Mountains.
at that moment it rains cats and dogs, the Minister of the Environment puts on his boots and goes to visit the city which has been flooded. There you have it, that's a seminal episode, and the end has now become mandatory. So one question that obviously arises from the moment that you have a warming surface temperature, you will therefore have a Mediterranean that will stay warm longer. Question, will it not increase this kind of episode? So the answer is that for now, it's complicated to say. It is not completely sure that this is the case.
And you have here a long series, which is made by the French Weather Agency,
On the number of seasonal episodes in France, with 2 cumulative thresholds. So you see here 190 and 150, and you see that it is not clear that at the moment there is something frankly on the rise. On the other hand, what is certain, and so this is a second thing to have in mind with regards to the consequences, is that the quantity of goods to flood increases. Because France is still in the process of urbanization, that is, the size of cities continues to increase, we continue to build every year a few 100,000 homes. So these accommodations, we put them somewhere, we don't put them on the additional floor of those that already exist, so we take up more floor space. And it turns out that in the south, like elsewhere, almost all cities have been built with a stream running through them. Because historically, it was access to drinking water or access to water that was used for something else, notably for washing clothes.
So you've heard of washing machines, so have I. They have not always been around.
In short, water was needed to water the cattle. Well, basically, we needed water. And so all the cities of France have been built on a stream of water, the biggest on rivers that were used as communication routes. When the stream starts to grow rapidly because there is a Sevenol episode, if you have things that are too close to the stream, boom, it's flooded. When you have a land pressure with new inhabitants who want to build, and that you have already built in all the places that are good, where do you give the permission to build in places that are not as good and especially too close to the stream? So you have additional constructions in increasing numbers which put themselves where they should not because the elect are not able to resist the pressure of the voters, and at this moment when there is a flood there are more things that break. The funniest thing that I've seen is a fire station, so where usually firemen are mobilized against the flood, which was flooded. So there. So there we were in physical parameters. So at this point, I summarize, the temperature will rise, not everywhere in the same way. It will increase, there is going to be more energy that heats the ocean than energy that heats the atmosphere, and it will impact the rainfall patterns. Now we are going to focus on a first consequence on the living things, because again, that's what really interests us. And here you have a map that represents the type of ecosystems that you have today on the surface of a planet if we do not cut them to do something else. And you have, especially here, a diagram which gives you the kind of ecosystem that you will find based on the precipitation and temperature. And what you observe, and that's why it's important to have a good visibility on precipitations, is that you change much faster the type of ecosystem if you change the precipitation than if you change the temperature. This is why, in fact, the essential point in the current climate change is not so much the variations in temperature as the variation in precipitations, which derive from it, obviously. But it is mainly this that will be essential. So the vegetation will change, and unfortunately it is not going to change in general in the good direction, meaning that we are going to have a lot more disappearances than creations because the time it takes to create something is a lot longer than the time it takes to disappear. The simulations that I'm going to show you now are necessarily partial simulations because the phenomena which are the most damaging for humans and for plants, it's not so much modifications, more exactly, it can be modifications of physical parameters. So for example, if there's no more water, plants will die. But you may also have variation in competition between species, which generates huge damage. And in competition between species, you typically have what is called pests, so insects, microbes, viruses, fungi. And so when I'm talking about fungi, it's not edible mushrooms. I'm talking about oidium, mildew, and other nice things like that. Well, these processes are extremely difficult to model. In other words, what is the fraction of oaks that will die because they will be victims of powdery mildew attacks at the wrong time in a warming climate? There's not a single model today that can tell you this sort of thing reliably. So the precautions to have with what I will show you is that these are lower bounds, not upper bounds. This is how to understand it. Here you have a distribution of beech trees in France today. So the higher the density and the more we go towards the red, and otherwise it's low. So basically you have the right to have beech trees everywhere in France, but overall you have it more easily here than there, and more easily in the Pyrenees than there. And so on the right, you have a distribution of beech trees that you could have in 2100 in a climate that is modified by the lowest of the emission scenarios that we have seen so far. So what you see is that there's a whole bunch of regions in France where it's no longer possible to have beech trees, mainly because it's too dry. Same distribution for the fir pine tree. So the fir likes places where it's cool in winter, and you see that cool in winter is more difficult in a climate that is modified. So you have places where you can have firs that shrinks. Here is another consequence of global warming. Here you have the flammability of forests today with 3 indices. So there and there it burns very easily, there and there it still burns reasonably easily, and elsewhere for the moment it doesn't burn. So this is today, and that is in 2040. Well, you see that in 2040, the flammability of the Fontainebleau forest, which is there, is that of the Aquitaine today. So there will be forest fires in Fontainebleau. Unfortunately, I really like the Fontainebleau forest. What you see is that the Aquitaine will burn as easily as the rim of the Mediterranean basin today, and so on. And I'm not happy to tell you that. I'm telling you this because it's unfortunately what will happen. So remember that. At 20 years old, I didn't, or I don't think I told you that. So I'm going to, because it's something that's essential. So I'm going to come back a little bit to tell you that. I'll go back here. So you don't see it well on this graph, but still, what you see is that all the simulations for the future, within the next 10 years, even if we stop emissions, and within the next 20 to 30 years, whatever the emission scenario, if we increase them, the trajectory is exactly the same. So basically, what will happen in 2040 has become totally independent, or is totally independent of what our emissions will be from now on. What will happen after 2040 will start to be differentiated according to our emissions. But you see that before, there is no difference depending on the emission scenario. So there is an absolutely major consequence, which is that in this matter, and this is obviously one of the difficulties of the problem at hand, in a way, with regard to the mitigation of climate change, we are working at best for our children. All right, we are working at best for our children. Regarding adaptation to climate change, here we are clearly working for ourselves. So the fact, for example, that from now on, I'm going to go put in the Fontainebleau forest all conceivable mechanisms that will prevent it from burning, that's something that we do for ourselves, for our own generation. Asking the French, the Germans, the Chinese, the Indians, the Americans, and the Russians to emit less so that the Fontainebleau forest burns a little less easily, that's something that we are doing for the following generation. Is that clear? Yeah, unfortunately, because of the inertia of the system. So we continue with the consequences. Here you have a graph, once again complicated, because all IPCC charts are complicated, or very rich in information to be more exact, which gives you by type of species. All right. So here, for example, you have rodents, and here you have mammals, I think, and here you have insects, and so on. So by type of species, and here you have trees, which gives you the possible migration range of the species in kilometers per decade. In other words, when I will warm up the climate, I will push the climatic zones towards the poles, all right, in terms of temperatures. So where I had the temperatures that I have today at 45 degrees, well, I will find them in a few years or a few decades at 48, 50, 55 degrees of latitude. All right? So I'm going to push the favorable zones towards the poles. And so if I want my species to survive, they must be able to migrate at a speed at which the zones are moving, at the speed at which you're going to move the climatic parameters. And what this graph will gives you are the ranges or the speeds at which these species can move in kilometers per decade. What the horizontal black bar represents is the average, let's say, per category of species. It's a sort of average. And here you have colored strokes that give you the speed of displacement associated with the different emission scenarios. So basically here it says that in the RCP 2.6, so therefore the lowest emission scenario, on the plain areas, well, on average, it will move at that speed, and so on. So there you have the globals for these scenarios. In the plain areas, what you see is that where it is flat, it will move faster than average, simply because where you have mountainous terrain, you do not have to climb up in latitude, you can climb in altitude. So the species that you have in the Alps will stay in the Alps, except that it will be higher in altitude, all right? On the other hand, in the plains, it will be pushed towards the poles. What you see is that, for example, when you are in RCP 6.0, well, you have a speed of movement towards the poles which greatly exceeds the average possible speed of movement towards the poles of trees. Because an oak tree takes 40 or 50 years to be sexually mature, so it can't, jump around like a flea every year to move towards the poles, okay? It must wait to go through the next generation before it can move elsewhere. All right? So what this graph tells you basically is that in RCP 6.0 or even in RCP 4.5, you will basically lose most of the forests. That's what it tells you. As far as herbaceous species are concerned, it's the same. You will lose part of them. On the other hand, some mammals, and of course, if you run out of food for mammals, this stuff becomes partially virtual, and so on and so forth. And so what you see overall is that for the basis of ecosystems, meaning plants, you have a possible migration speed of these ecosystems towards the poles, which is much lower for the majority of species than the speed of movement of climatic parameters that will be observed. So that's what this diagram tells you. And so when we say that it will be a loss of ecosystems, it is exactly due to that. There you have a graph which talks this time not about wild ecosystems but managed ecosystems, that is to say agriculture. So agriculture is a managed monospecific ecosystem, that's it, meaning you have a single species, so monospecific, the one that grows, that interests us, we don't care about the others. So now it's a little less true because we are trying to start doing things differently. And what this graph gives you is the current trend, and I do say the current trend, on the variation per decade of agricultural yields. And what you see is that already today you have two species, which are the wheat and the corn, on which we already have a downward trend on the agricultural yield. And you see the four main cereals grown in the world, so wheat, soybean, rice, and corn, with an annual production of around 2 billion tons, or a little over 2 billion tons. And so you see that at the moment, in any case, there is not one which benefits from it. Here, it gives you the prospective results. So the prospective results when you do simulations is that we expect, with an important error bar, of course, that the agricultural yields will continue to decrease in the future under the effect of global warming. And you see that where it could decrease the fastest is in the temperate regions if we do not have any adaptation measures. Except that in adaptation measures, you have, for example, irrigation, and irrigation is not necessarily something that is easy to implement, because if it stops to rain significantly, well, if it rains less, irrigation is not necessarily much simpler. And this is something that is absolutely major
On a planet whose population, on the other hand,
tends to increase for the time being, because I remind you this old saying once again, which is at the origin of a revolution of 1789.
a hungry stomach has no ears.
In other words, when people don't have anything to eat, they go crazy, and this is normal. And this is normal. So the fact that agricultural yields are decreasing, and to answer the question from earlier, when does this either cause migrations or wars, or I have strictly no idea, or like riots or revolutions, no one can tell you. Anytime between now and later, so there. These are typically things that will take us by surprise, and it is absolutely obvious. So some of the surprises will come from there. Yes? Yes, it is interpretable. There's a big risk. So I repeat, when there's a big uncertainty, there's a big risk.
It means that you can't rule out that my cursor is pointing.
And by the way, last year in Europe, in 2018, you had a yield drop of 20 to 30% in certain crops. So in potatoes, part of cereals, etc. In Russia in 2010, you had a drop of 45% of grain production. And this is the start of the 21st century. So there may be increases, except that if you compare Russia and Poland, this is not the same cultivated areas, this is not the same tonnages, okay? And besides, it does not serve the same markets, it is not necessarily the same grains, etc. And so no, from my memory, in potato last year, everyone suffered. No, these are annual variations. So as long as you have stocks and the energy resources to have stocks, meaning fridges, things, etc., it is not a big deal. In the Middle Ages, when we didn't have the means to have stocks, if we had a 40% drop in production in a given year, people would, starve and revolution. So here, for the moment, it is abundant energy that allows us to adapt to a lot of things that refer to the second course. Abundant energy is not eternal. And the essential or most of the consequences of global warming will intensify in the second half of the 21st century at a time when abundant energy, in part, will no longer be there. So there is going to be a pincer effect. This is also why the consequences are particularly difficult to predict. In general, people who are interested in the consequences of global warming, they reason, like many other specialists, all other things being equal. So for them, there's not a shadow of doubt that there will always be effective fertilizers, tractors, phytosanitary products, cold chains, etc. Except that it's not for sure. Or more exactly, it is certain that it will be the other way around after a while. It's just a matter of time. So in the other consequences of climate change, we will change the microbial biodiversity. So something that is easy to understand is that when you heat a culture broth, as long as we don't heat it too much, but just heat it a little, the little creatures love that. And so in a globally warming world, we're going to tend to favor the increase of microbial biodiversity, which has a tendency, as you can see here, to be higher in the warm places. So that's the ink bottle. That is to say that apart from telling you that, I'm not able to tell you much more, but it's obvious that there will come a time when there will be novelties with regards to diseases, and of course, this isn't the only trigger of new diseases, far from it. So I won't detail on that, only that. This is because this is funny. Well, it's not funny at all, but you have here for Bangladesh, at the top, the variation of cholera cases. And at the bottom is the variation of the surface temperature of the Pacific water. So what you see is that when there is an increase in the surface temperature of the Pacific water, so in this case the Eastern Pacific, you have an increase in the number of cholera cases in Bangladesh. Do you know what the temperature rise in the Eastern Pacific is called? It's called El Nino. When you're in El Nino conditions, you tend to have a change in the rain regime, and therefore you have what was I saying? You have an increase in brackish water in Bangladesh. That is, waters that mix seawater and fresh water. which promote the development of the Vibrio cholerae, so you have more people who are sick from cholera. So here is something no one, I think, would have been able to propose a reasoning of this nature in advance. That is to say, when there's an increase of the surface water of the Pacific, bam, you're going to have more cases of cholera. There you have it. So this is typically the kind of consequences that you can understand afterwards, but it's very difficult to predict before. We will now talk about the rise of sea level. So here you have a schematic representation, very schematic even, of emerged land with mountains on which there are glaciers on some, of oceans, and of ice caps, which you have here. So all of this participates in the variation of the water level. The first thing that will happen is that with water is that, as I told you earlier, the quantity of heat stored by the water increases. Hot water tends to take up more volume than cold water since water expands when it heats up, and since the bottom of the bathtub still doesn't vary, it means that the level of the water in the bathtub increases when you heat the water, and so the water level rises. The second thing that will raise the water level is when you melt an ice cube, which is placed on land. So you have a first ice cube or series of ice cubes placed on land, which are the glaciers of the mid-latitudes, typically the Mer de Glace, for those of you who have been to the Mer de Glace. And so it's in Chamonix, and you may have seen before taking the Montanvert trains to, go back to the train station. There are metal stairs, and along these metal stairs you have signs which tell you how high the Mer de Glace was 10 years ago, 5 years ago, 20 years ago, etc. And it's extremely spectacular. It loses a few meters every 5 years. I mean, it's going at an incredible speed, in thickness, of course. And so this water, since it is no longer in the Mer de Glace, well, it ends up in the sea. Then you have the caps, which will have an impact on the water level. So the caps can have two types, or three types of impacts more exactly, on the water level. So there are two that are represented here, and the third I will talk about it later. The cap goes from 50,000 meters in altitude to the sea level, roughly, since where it calves icebergs, where it ends, it's at sea level, and at the summit of the cap, it is an altitude of 3,000 meters. So it's like, to take the link with the Mer de Glace, it's like between the Chamonix Valley and the summit of the Mont Blanc, it's not exactly the same temperature. At the bottom of the cap, you will frequently have positive temperatures. At this time, the ice melts and contributes to the rise in sea level. But at the top of the cap, you often have negative temperatures, or even constantly negative temperatures, and so there, the snow falling withdraws water from the sea. The water was in the sea, it evaporates, it falls on the cap, and it stays on the cap, so that lowers the sea level. So with regard to the caps, it is necessary to make a mass balance, which is what falls there minus what goes there. And it's the difference between the two that tells you whether the ice cap is contributing to the sea level rise or the sea level drop. Right? So when the ice cap forms over Scandinavia, obviously what goes there is more important than what goes there, and the sea level drops. This is what I showed you earlier. Today, it is rather the opposite, so what is happening there is superior to what is happening there, and therefore the cap contributes to the rising sea level. The melting sea ice, since you all know Archimedes, has no impact on the water level. When you melt ice that floats already on the surface of the water, Mr. Archimedes tells you that it does not move the water level. On the other hand, Mr. Not Archimedes, that is to say the physicist, tells you that it still has an impact because you're replacing a particularly reflective surface, which is sea ice, by the particularly absorbent surface, which is seawater, which accelerates the heating of the seawater around the cap. And that accelerates the melting or the disintegration of the cap. So there is no direct effect, but there is an indirect effect. The sea ice, in this case, is melting. That is to say, and it's the same in your lifetime, as long as there will be newspapers and people to talk about it, well, regularly, maybe not every year, but every few years, we will tell you, we just broke the record of minimum sea ice extent of late September. So there, Because the process has started, and it will continue because the rise of temperature is, as I said earlier, more pronounced in the Arctic than anywhere else. There is also a decrease in the thickness of the sea ice, which is in progress. So not only does it decrease in extent, but it decreases in thickness. So we know the thickness of the sea ice since the 1970s. Do you know why? Who had the means to go and measure the thickness of the sea ice since the 1970s? No, not the oil. Worse than oil. People even nastier than the oil companies. Not the Chinese, no. The Chinese only have one oil company. Yes, military. Which military? Yes, absolutely, the submariners. The people who operated the ballistic launcher submarines, that is the poetic name given to things that shoot nuclear missiles, well, they measured the thickness of the sea ice to see if they could be able to surface at any time while wandering under the sea ice. And so they measure the thickness of the sea ice. And so we have records, a long series, over several decades on the thickness of the sea ice, and this is how we know that it decreases. But the biggest potential unpleasant surprise for the centuries to come is not from all that it will come, it's from the caps. Greenland has started to melt. We know that Greenland began to melt, first of all because people walk around on it, and above all because we are able to do radar altimetry, that is to say that there are satellites that roam in the upper atmosphere, well, a few hundred kilometers from the Earth, and which may measure with radars the thickness. They do altimetry, so they measure the thickness of the cap. If the thickness of the cap decreases, it's that the cap started to melt. Once the cap begins to melt, the process self-accelerates, and it self-accelerates for several reasons. The first is that when the cap melts, its summit loses in altitude, and when its summit loses in altitude, it is surrounded by warmer air, and therefore it melts even faster. The second process by which it self-maintains is that at the top of the cap, you have dust which is carried by the wind. These dusts absorb solar radiation, and the snow on the surface is melting, but the dust doesn't. So the more it melts, the more the dust concentration increases, since the dust have been brought continuously with the snow, and you end up with a dust density on the surface that increases, and therefore a surface that absorbs further solar radiation, and bam, it further amplifies the process. And then you have a process of melting sea ice, which also increases the temperature in an accelerated manner. And so once it starts, it doesn't stop. So the Greenland ice cap is set to melt, partially or completely, in the centuries to come. As far as Antarctica is concerned, you see here as well the result of a radar altimetry, and you see that West Antarctica, and in particular this part of West Antarctica, has also begun to lose volume. And so there, the process at work is a little different. It turns out that West Antarctica rests on a bedrock that is underwater and which is draining. That is to say that the further you get from the coast, the deeper it is, all right? As long as you have the terminal bits of the glaciers that begin to retract, so because the temperature of the sea rises and that the sea level rises a little, well, you have a process of destabilization of ice which is eaten away from below, which accelerates, all right? And in addition, this West Antarctica is placed on a base which has a slope, and so it's a kind of flying buttress system. Each glacier roughly consolidates the neighboring glaciers, and when you have the terminal glaciers which are near the sea which begin to destabilize, you have the flying buttress system which begins to destabilize, and so there is a possibility that West Antarctica will completely disaggregate in a few centuries if the temperature increases by more than 2 degrees. And so since the temperature will rise by more than 2 degrees, well, I'm skipping that part. Well, it is quite likely that we are going to set in motion a partial or total disintegration here as well of West Antarctica on the scale of a few centuries. So here you have simulations that were done recently, so this one is 2016. And what you see is that with the scenario in which we no longer emit tomorrow morning, everything is fine. But with the 4.5 scenario, although it is not a very emissive scenario, well, we already have a possible contribution from Antarctica of 5 meters in the coming centuries. And with the more emissive scenario, we go straight up to 12 meters. So with the 5 to 6 meters here at more than 2 degrees, we are reasonably sure that will happen. At the same time, we'll take 3 to 6 meters from Greenland, and at the same time, we'll take at least 1 meter on expansion of seawater because of temperature. Yes? So it will not necessarily be homogeneous. and I'll come back to it later. So to give you an idea of what it represents, a few more meters in the world ocean, you have here a map in which we have put in dark blue places that will drown. So here you have Bangkok, for example, which will drown with a rise of 9 meters of sea level. And so here you have Shanghai, wait, no, I don't remember. This is Northern Europe. So there you have it. We were talking about migration earlier. Well, well, you see that the Flemish are going to invade the Walloons.
You know, they don't get along as it is, so
that's not going to improve. So until about 6 months ago, what came from the scientific community was it is a risk at the horizon of a few centuries. Since about 3 or 4 months, there are publications that came out with people saying that it could go faster than we imagined. So faster than we imagined is not next week, but maybe already in a century, very significant things will happen. So here as well, we have entered a big question mark, and the how to say this? The great particularity of this question mark is that no one can answer it, so no one can give you a lower bound of the troubles to come. I insist on it. A big uncertainty, I insist, is a big risk. So question, will it manifest itself continuously? Reply, no. So today you have an idea for those of you who have already been in Brittany, so excellent region by the way. So you can imagine the increase in water level, that's like the tide rising in the beach, okay? So it's very subtle, very subtle. And in general, you're at the beach when the weather is nice, not when there's a level 10 storm. So you see it's nice, it's not too windy, etc. And the thing goes up slowly, but hey, if it gets your feet wet a little, you just pull the towel back and it's okay. So we tend to forget in this image that after water goes up, it goes back down, that it does not rise above a certain level, and that it happens when the weather is nice and gentle, etc., and that it only concerns sand because you have the high seas leash, which is still sand, and so the whole foreshore is covered with sand, and it's an area that is planned for that. Regarding the rise in sea level, things are going to present themselves a little differently because you have a billion human things that are of interest to man that are built by the sea. So you have harbors. In general, harbors are not placed inland. It's more convenient to have them by the sea, except that harbors cannot withstand an indefinite rise of seawater, because if you have too high a rise of sea level, you will drown all the infrastructures that are in the harbor. So you have plenty of warehouses, stocks of all kinds, railway terminals, etc., all the things that don't like to be drowned in seawater. So you have refineries, because a large part of the refining concerns petrol that is brought in by tankers, and it is more convenient to have a tanker on the water rather than in the middle of the both regions, so refineries are by the sea. You have a lot of electric power plants that are by the sea for cooling. For example, all the electric power plants in Japan, not just nuclear, are by the sea in first approximation. You have agricultural silos, because a good part of the trade in grain is done by bulk carrier. So agricultural silos, you have a good part which are by the sea, etc. And so you have a lot of important stuff that are by the sea, and so you also have a few cities. So you have a lot of things that are by the sea, and these things are protected against the aggressions of the sea. Because from time to time, the sea is a little nasty, so you have a storm with a big depression, and so the water level rises. And for those of you who watch the aftermath of storms, you usually have what are called surges during storms. That is to say that the level of water rises dramatically, and this rising water level can drown a whole bunch of stuff behind it. So what will the rising water level do? It will bring closer to the seaside all the infrastructure I just mentioned, and it's on the occasion of an extreme phenomena, as there always has been and always will be. At this moment, the sea passes over the defenses and makes huge damages behind. So the rising water level will not produce consequences that are gentle and continuous. Alright, this is not how it's going to happen. It's going to happen on the occasion of discontinuous violent phenomena. This is how the phenomena will occur. You also have in low plains sometimes the conjunction of a storm, because this often happens in winter, and terrestrial floods, because it rained a lot. And at this moment, it is the conjunction of the two which brings water from one side and the other, and bam, you have a process which is particularly destructive. So I'm going to skip that because I don't have time. You also have in the consequences that are possible, so I'll come to Greenland in a second, a large-scale modification of the circulations that you have in the ocean. because of the trade winds, which constantly push the water in the same direction at the equator, and from the Coriolis force, you have a great movement of circulation in the oceans of the world, which is organized roughly as follows. It is a great east-west movement on the surface, going around Africa by the south, and a great reverse movement in the depths, with here the water, diving. So why does the water dive south of Greenland? Because it turns out that water is particularly dense when it is particularly cold and particularly salty. Therefore, in the south of Greenland, you have water which is enriched in salt because when it went up north through the Atlantic, evaporation led in part to precipitations which ended up in Europe and which did not flow to the same part of the Atlantic, so the rivers bring fresh water, not in the same place where the water came from, where it lost fresh water and became more salty. And so when you get to South Greenland, so you are in an ice-forming region. When the sea ice forms, so sea ice is frozen salt water, but it is less salty than the seawater from which it was born. And so it expels brine as it forms, so seawater forms and it expels brine, which means that water that doesn't freeze suddenly becomes saltier. And at this time it becomes particularly cold, it's winter, and particularly salty, and it dives. It becomes denser than the water that was below it, and it dives. This deep water dive is like a siphon, all right? It is a downward movement, which is like a siphon, and it's because of this siphon movement that you have the North Atlantic drift, which goes up to the south of Greenland. Moreover, since this movement buries surface heat, it's because of that the warming is less pronounced in the south of Greenland, because you have a heat pump that takes the heat from the surface and buries it, whereas this heat pump does not exist in the rest of the ocean. All right? And it's the existence of this heat pump, in the truest sense of the word, I mean, it pumps heat, that you have a warming which is less pronounced as long as this deep water dive takes place. Of course, if this deep water dive stops, and it is a question, it might happen, at this time, the heat loss from the surface by burial stops as well. And then you no longer have that singularity in South Greenland. That tells you the same thing in cross-section. So question, could this circulation weaken? The answer is yes, because in a world subject to global warming, well, the warming of the tropics is less important than the warming of the Arctic, and so the difference in heat between the Arctic and the tropics weakens, and therefore the fact that it weakens decreases a bit the potential difference between the two, and so it's going to weaken the circulation. And so what the simulations show you is that almost all expect, so that is a decrease in the circulation of the North Atlantic drift. So the North Atlantic drift is expressed in Sverdrup. These are millions of cubic meters per second. As a reminder, the flow of the Seine River is 400 cubic meters per second, so we're not talking about the same orders of magnitude. Well, there are many who think that it will decrease, but there's no one who thinks it will stop abruptly. However, there have been episodes in the past where this circulation has stopped abruptly during ice ages, at times when there have been huge iceberg breakouts that took place in the North Atlantic, and that brought so much fresh water that the water was no longer dense enough, because it was no longer salty enough, to be able to dive. And at this time, the circulation stops. And we can see it with very rapid modifications on very short timescales of vegetation by finding pollens in the core drill samples of sediments near the coasts. We realize that the vegetation has completely changed in a few decades. And this is attributable to a modification of this thermohaline circulation. Other consequence, extreme phenomena are expected to intensify, and it's a process which is already at work. As I said earlier, I mean in the previous lesson, extreme phenomena are linked to a convection between a hot surface and a cold stratosphere, and with a stratosphere which cools down and this surface which heats up, and an evaporation which increases, overall you have an intensifying convective pump. All right, and so logically we expect that everything such as tornadoes, hurricanes, etc., and cyclones increase. So what we observe is that the number of cyclones in the North Atlantic has a tendency to slightly increase, but above all, their intensity tends to strongly increase. Here you have an evolution of the intensity of cyclonic phenomena in the Atlantic, and you see that the phenomena of categories 4, and 5 have considerably increased over the last decades. So in other words, for the moment, there are maybe a few more cyclones than before. It's not very clear. On the other hand, what is very clear is that you have more intense cyclones that appear. And in fact, that's exactly what we're expecting for future warming. You have here a map, well, it's by basin and then for the planet as a whole, but hey, I'll just give you that directly. The important point is that you see the precipitations and the winds will tend to increase in intensity. In other words, there will not necessarily be more cyclonic phenomena. On the other hand, on average, when they will form, they will tend to be more destructive. Other question that is asked, are we going to modify the El Nino-La Nina oscillation? At the moment, the answer is not clear. There's a bit of beginning of a trend, but there. And this is also a question because it will amplify the, let's say, 10-year extremes, because the more intense El Nino and La Nina are, the more you have extremes that are important compared to the trend. Other consequence of what is happening, the ocean will become acidic. So the fact that the ocean is acidifying is something that is physical. A part of the CO2 goes into the water. This is a partial pressure balancing. Once the CO2 went into the water, it makes a reaction where it will lead to the formation of hydrogen carbonates, I think that's how we say it nowadays, and H plus ions, so it will acidify the water. So you know that CO2 in ancient times was called carbonic acid. If you read Jules Verne novels, that's what it's called. So I put more CO2 in the water, I acidify the water. It turns out that what the acidification that we are about to do is something which, again, is extremely disruptive compared to what the pH of the ocean was, at least over the past 25 million years, which was remarkably stable. And here you see how the pH can evolve over very, very short time horizons compared to geological scales. So obviously there are a number of animals in the ocean which are accustomed to this very stable pH, starting with corals, but also starting with a number of species which need to synthesize limestone, and in particular aragonite. So aragonite is a form of limestone, so you have two forms, calcite and aragonite, which are synthesized by a number of planktonic species to make small shells. Well, if they can't make these little shells anymore, these species disappear, they die. So part of the plankton is at risk in this story. So I'll skip that because I don't have time. And I'll skip that too because I don't have time. So at the end of a chain, there is us. This graph is there to remind you that the health risks, that is to say the risks for the human species, they come both from things that we have seen so far. Again, if we don't eat, we are not okay. And then they can come from indirect risks, that is to say, if it is the neighbor who can't eat, the neighbor begins to go in a state of war and the neighbor arrives at our place, so we may have enough to eat, we will still be at risk because of climate change, because we are going to have a consequence that is not a direct physical consequence, but a geopolitical consequence. I do not believe that there is a reliable software for war forecasting. Well, in any case, in medium and long term, I don't think it will be very simple. On the other hand, something which is reasonably robust as a conclusion is that from the moment you have a how to put it, you have a global pressure buildup of the system. That is, you have, like in the plate tectonics, people who are globally under increasing stress on the surface of a planet. It is not very difficult to understand that basically the conflicts will increase. Not very difficult to understand that it's globally going to be the case. Last point, I will now show you the causal effects around the carbon cycle and the climate, which is an important thing in what concerns us. So here you have a diagram that represents the flows and stocks of carbon on Earth, with in black the situation as it was before mankind did something to the climate, and in red modifications which intervened in the mid-1990s in relation to the pre-industrial situation. So what this graph tells you is that, for example, in the pre-industrial situation, the ocean exchanges carbon with the atmosphere. Why? Because it turns out that the seawater's ability to dissolve CO2 is higher when the water is cold. So anywhere on the surface of the Earth where you have currents that cool the water, you have a downward flow of CO2. So for example, the Gulf Stream is, or rather the North Atlantic Drift, more precisely, is a CO2 pump. The water cools down while it goes towards Greenland, and so it pumps CO2. Conservatively, the Labrador Current, which is a current that comes from the North cold and whose water heats up while going south, that is a CO2 emitter. Obviously, the CO2 which has been absorbed in one place is remitted in another, and the system balances. You have a second natural flow of CO2 between the atmosphere and emerged land, which is the cycle of vegetation. So to grow, plants take carbon in the atmosphere as CO2, but afterwards the plants are eaten either by macroscopic animals, you for example, or by microscopic animals, it is the decomposition of dead plants, and at this moment respiration releases this CO2 to the atmosphere. And in respiration you obviously have microorganism respiration. What you notice is that before we fiddle with the system, the flows are globally balanced, so you do that and that and that and that and the runoff here, and bam, it's balanced. So runoff is the leaching by rainwater. And then come men and women. So what do? We are going to do two things. We are going to deforest and we are going to destock fossil fuels. So in both cases, we'll take carbon that was in a stock, vegetation or fossil fuels, and stick it into the atmosphere. In doing so, we increase the amounts of CO2 in the atmosphere. In doing so, we increase the temperature of the atmosphere. At this time, since the temperature rises, the surface water heats up, and that, all other things being equal, sends more CO2 into the air. It is the process I told you about at the time of natural variations of climate, when I said when astronomical parameters warm the climate, it sends CO2 into the air and it amplifies the process. But at the same time, since you have more CO2 in the atmosphere than in the ocean, in partial pressure, you will create a downward flow of CO2 from the atmosphere to the ocean. So it turns out that, by luck, so to say, currently the two are roughly balanced. But it's luck, because one comes from a partial pressure difference and the other comes from a temperature variation. So yeah. Regarding emerged lands, initially, more CO2 in the air, it's more food for plants, so the plants have a tendency to increase photosynthesis. This is how we speed up the metabolism of tomato plants in the greenhouses in Nantes. It's by enriching their atmosphere in CO2, thanks to what a kilo of Nantes green tomatoes is almost a kilo of gas. But at the same time, you have an increase in the temperature which promotes microbial metabolism, and therefore the respiration of microbes, so the emission of CO2 by emerged lands. But over time, it turns out that the increase in temperature will intensify after the CO2 stops increasing, and at that point you're going to have an intensification of the carbon emissions by soils. You're going to have a weakening of photosynthesis because ecosystems will increasingly have difficulty supporting the rise in temperature and water stress. And with regards to the ocean, you are going to have an intensification of CO2 released by the water at the same time that the partial pressures will end up balancing out, and therefore that the downward flow will come down. So what I'm showing you is that you have here a set of positive feedback loops, you see, which unfortunately gives the system the ability to get carried away because of the climate feedback on the carbon cycle. So it will always end up damping out, it will always end up finding an equilibrium point, but unfortunately this equilibrium point is likely to be found much too high. And I will end with characteristic timescales of this matter. Here you have a perspective on how the various processes which I told you about are going to be staggered in time regarding this matter. So here you have how the CO2 emissions are going to evolve. You see they're increasing, and at the latest, because of the geological limitation of stocks of fossil fuels, it goes through a maximum and then it decreases. And I do say at the latest because of that. It can decrease sooner, and we must hope so if all the consequences I just mentioned don't seem attractive enough so that we decide that it's worth the hassle. Because of the chemical inertia, so CO2 is an oxide, therefore chemically stable, because of the chemical inertia of CO2 in the atmosphere, you can see that it is not when we pass the maximum of emissions that we pass the maximum in concentration. So when the emissions start to decrease, that is to say when you are either under energy stress or either we start to make efforts, one side or the other, in every case, the first thing that people will see is that the concentration will continue to increase. So it's a complicated situation that, as you say, shit, either we are in more and more trouble and we see that the concentration increases anyways, because we don't have enough energy anymore, or we'll have started to make efforts and we see that the concentration increases anyways. Either way, it's going to be a complicated situation to explain. The temperature will continue to drift long after we have passed the maximum of emissions, very long after we have passed the maximum of emissions. And finally, with regards to the response of the oceans and the cryosphere, the consequences will scale over thousands of years after we have passed the maximum of emissions. So I repeat what I said when I spoke of chemical inertia of CO2 in the air. In fact, climate change is a system in which there is no way to heal. So we can prevent, we can adapt, but we cannot heal in the sense that we cannot remove the cause of a disease. That's what you need to keep in mind. So what I say again, even if it's not overly sympathetic to the generation that you eventually represent, is that it is a process which will unfortunately only grow and embellish until I die and until you die, whatever we do in any case. That we work for our children with regard to the damping of the consequences, but it is on this scale that it happens. That we must be careful not to think that what we do not know is an absence of risk, because in general that's how we reason. Unfortunately, that is not the way to reason in the present case. And finally, the last sentence loops back to the first lesson, and it is absolutely essential. A significant part of your life will be spent in a world in which access to energy will become a growing problem for an increasing amount of areas around the world, which means that the capacity to respond to the problem will tend to weaken with time. This is another way of saying that we should allocate our resources to taking care of a problem while we still have some, instead of thinking that time plays in our favor and that tomorrow we will have drones, robots, and God knows what artificial thing that will make it possible to deal with a problem more easily than today. Alright, in fact, since it is energy which is in first order of a proxy of our ability to manage anything, if we have less, it is not, unfortunately, essentially a technical findings that will compensate for that at first order. It won't work well. There, so see you next time.